So this is a question that goes back to unit 3. I have to keep thinking about our units. So not that you're necessarily thinking about units, but it's going back to scatter plots when we were learning about correlation coefficient. And the correlation coefficient, maybe the main takeaway from the correlation coefficient is that it is an inherent property between two variables, and no matter how we transform the data, the correlation does not change. So if you started off with a correlation of 0.28, you're going to end with a correlation of 0.28 no matter what you do to the data. In fact, when we find the correlation, essentially what we're doing is we're doing our own transformation, if we use the formula, to convert everything to z-scores in the first place. So doing any kind of transformation, just like we do when we turn data into z-scores, it does not change the correlation. At this point, I'm repeating myself. So the most common wrong answer here was C, and that makes sense because you're probably thinking about like, oh, okay, well, it's probably not affected by adding a number, but doubling it might double the correlation. But turns out, no, it does not have an effect. Okay. So that's some good review. Okay, so we are going to be looking at chapter 17 formal today. So if you have not been reading through chapter 17 at all, that's okay. We're going to talk about it, but highly recommend that you go through and read because we're dealing with, you might at the end of this determine it's pretty straightforward and pretty simple for you. You might find it challenging. Of course, that's true with anything in stats. So let's just jump into it. So I wanted to make sure it's very clear that how the book is processing this. If you've been going through doing the work, you are hopefully feeling good about it. The way that the book uses its notation, this is a rescaling, and we did a practice problem with this yesterday, where we would just be multiplying the mean and the standard deviation by the constant. When it's like this, it's saying it's multiple events of the same thing. And this is where we'd have to use our Pythagorean theorem, where it's going to be 12 squared plus 12 squared plus 12 squared in order to get the standard deviation. I'm not going to go into more detail with this one. Just wanted to clarify in case that was lost on you. And if that's still lost on you, stick around. We can talk about it more. But I wanted to say one more thing. Ideally, on the AP test, those of you who are doing that, you will not see a question that looks like this because, like I said before, it's hard to know what they mean if it says 3x. Do they mean 3 different events or scaling one event by a factor of 3? All right, this is more straightforward as far as figuring out what they're asking for, not trying to interpret notation. So the American Veterinary Association claims that the annual cost of medical care for dogs averages $100 with a standard deviation of 30. For cat, averages $120 with a standard deviation of 35. What's the expected difference in the cost of medical care for dogs and cats? So we're doing a combination of random variables, and this is going to be, so if I use D and C for dogs and cats, the difference between in medical care for dogs and cats, so I'll just do D minus C. Or maybe I'll do C minus D. It doesn't tell me in which particular direction it's supposed to go. So yeah, let's do C minus D because cat care, it looks like costs a little more. So C minus D, the expected value of C is 120 with a standard deviation of 35. The expected value for dogs is 100 with a standard deviation of 30. So luckily we learned yesterday how we can combine this. I'm just going to run through it pretty quickly. So the expected value of C minus D is just going to be 120 minus 100. The expected value is the easy part. So the expected value, the expected difference between them is $20. But the standard deviation for C minus D is going to be the square root of the variances. So that's going to be 35 squared plus 30 squared, which gives me, you can plug this in at home as well. That gives me 46.10. Sure, I'll call it that, 46.1. So there we go. We answered the first part. What's the expected difference? And the second part, what's the standard deviation of that difference? All right. The third part is the reason I wanted to do this practice problem. It says, if the costs can be described by normal models, what's the probability that medical expenses are higher for someone's dog than for her cat? All right, so this scenario, keep in mind, if we have a continuous random variable, then that is going to be described by a normal distribution. One thing we didn't really talk about yesterday, but when you combine two normal distributions together, it creates a new normal distribution. So that's great. We don't need to worry about it. Oh, now it's bimodal or something else. No, normal, a normal and a normal combined together creates a new normal. All right, so if we're good with that, let's figure this out. We've got a new normal model that looks like this. So a normal model with the mean of 20 and a standard deviation of 46.1. So if I draw this, the mean right here is going to be your 20. Then it's going to be negative 26 essentially and positive 66. That's just adding 46 and subtracting 46 from it. So along the way, we get to this break-even point. I'm going to draw a 0 on about right here. All right, this is going to represent 0. Now, this is the point. Keep in mind what's happening because we're going to see stuff like this later. When we combine random variables like this, we need to remember what these numbers represent. The mean is the average difference between the cat and the dog care. So on average, it's going to cost $20 more for a cat. But there's going to be a region of this graph where it costs more for a dog than for a cat. And that's going to be where it's negative. So anything positive means the cat costs more than the dog because we did cat minus dog. So any positive number means the cat costs more. Any negative number means the dog costs more. So at this point, we want to figure out what is the area under the curve for our new normal model that we just created. So if you're following along with the logic so far, the last part isn't that big of a step. So let's see. 0 is our cutoff. We need to figure out the z-score for that particular spot. So remember, it's x minus mu divided by the standard deviation. So my x value of interest is 0 minus the mean is 20 divided by the standard deviation is 46.1. So I can figure out this z-score. Negative 20 divided by 46.1 gets me negative 0.4338. So this is the z-score for that particular value of 0, negative 0.4338. Okay. So again, if you're following from here, the only thing we have left to do is figure out what is the area from negative infinity up to negative 0.4338, and that is where we use normal CDF. It's a normal distribution, and remember that CDF is just the cumulative density function, which determines what the area is under the curve. So if I plug that in on the calculator, I'm going to go from negative 99 to negative 0.4338 with a model of 0 for the mean and 1 for the standard deviation. And that will give me my answer. So remember the second distribution if you're trying to remember where to find that function. And you're going to get a number between 0 and 1. In this case, I got 0.3322. So what does that number represent? And it's a rhetorical question. I'm answering it here. Remember, this is the area under the curve. This represents the probability. So there is a 33.22% chance that the dog is going to cost more in vet bills than the cat will? Okay. So if there are questions right now, we can answer them. If this is something you want to come back to, we can come back to it. The last question here is, what concerns do we have? And just to answer this one quickly so we can move ahead. The question is, are these independent? And if it's the same person that has a dog and a cat, they're not necessarily independent. They might have the same kind of care at home, which might make them, have similar conditions, except for maybe the food they eat. So they're not necessarily independent in this scenario. Okay, I'm going to skip that. What we're talking about in chapter 17, and this is the big thing, is what we call Bernoulli trials. And they talk about one of the Bernoullis. Is it Jacob Bernoulli, or I can't remember. There's lots of Bernoullis. And they all did impressive stuff in history, but they all hated each other. Okay, so that might ring true for some of you. All right, Bernoulli trials are specific things, and these are events that have certain characteristics, which are the outcomes must be binary, where failure or success are the only options. They must be independent. So each trial must be independent. That one's straightforward. And they must have the same probability for each trial. And there we go. That's why those are called Bernoulli trials. Now you'll figure out pretty quickly how we use this. There's Daniel Bernoulli. There we go. Okay, so we can do different things with, if we've determined that we're dealing with Bernoulli trials, we can do different things. And we're going to learn about one of those today. Okay. So let's start off with an example. In the 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, Memphis's Darius Washington attempted a three-pointer. He missed, but was fouled and went to the line for 3 free throws. Each free throw is worth 1 point. Was it smart to foul? And maybe we can answer that one right now. I mean, not answer it statistically, but just think on that. Was it smart for the team to foul? If it made him miss a three-pointer, but it gave him 3 free throws, was that a better option if those are your 2 options?
Yes.
Yes, I'm hearing. And maybe some of you at home are thinking, no, it wasn't smart. And maybe some of you are thinking, we don't have enough information to make that decision. So let's look into this more, and we will statistically determine if it was smart to foul or not. So the first question is, what are the possible ways that the shots could fall when he shoots 3 free throws?
He misses 1, he makes 2, he misses 2, he makes 2, he misses 1, and then he makes all 3, or he misses all 3.
There we go. So those are the main 4 outcomes. So, and let me just put it in. So he makes all 3, and I'm going to put pluses for makes, and he misses all 3, minus, minus, minus. Now he could make 2, which would be plus, plus, minus, plus, minus, plus, and minus, plus, plus. And he could make only 1. So that'd be plus, minus, 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 plus, minus, 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 plus. So of course that's miss, miss, minus, or miss, 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 make. Okay, I'm gonna mix up my words here. So these are, 1 make, 2 makes, 3 makes, 2 makes, 1 make, and then 0. So those are the outcomes. I think we're feeling good about that. All right, so let's go into this a little bit further. And maybe I should have done all this on this page. So let me just copy this down real quick. All right. And there we go. So it's important that we have this, because this is going to be important as we go through this. So find the probability. Now we're looking at the actual outcomes. This is the very last play of the game. And we actually have some clips that I don't think they're going to come through very clearly. It's going to be very choppy. So Darius Washington was a 72% free throw shooter. We're going to find the probability that Memphis will win, lose, or go to overtime. Overtime is when they're tied. So just to clarify, let me go back real quick. The score was, I didn't say the score, did I? The score was 75-73, I believe. Let me double check. Did I say it was 75-73? There it is. Yeah, 75-73. Okay. Let me go back to our current page. So, what is the condition that allows them to win?
If he makes all three.
If he makes all three. That's the only way they win. So we can figure this out. So it's a probability of 3 makes. So it's a probability of plus and plus and plus. And let's actually do the math right now. What's the probability that he makes a free throw?
72%.
72%. Okay. So we've got 0.72 times 0.72 times 0.72, and we can multiply that out. And feel free to write that on the screen. There it is, 0.37 essentially. And it's got some more precision, but 0.37 works for our purposes. Overtime, I'm going to skip lose for right now. What has to happen for them to go to overtime?
He makes 2 of the baskets.
Makes 2. All right, so we're looking at this right here. And now we've got the probability. And here's what the good thing about probability. As far as this goes, it doesn't matter, even though we showed that there's 3 different ways he could make 2, for right now, it doesn't matter the order because we're just multiplying the probabilities together. So it's the probability, I'll just say that he makes the first one and he makes the second and he misses the third. So this would be a, what was I trying to say here? Oh, these are all independent trials. And remember, we're talking about Bernoulli trials. So this means this is binary. Either he makes it or he misses. They're independent. We're going to assume that these are independent for our purposes and that he has the same probability of 72% each time. So if I do this, what am I multiplying together? Give me my numbers.
0.72, 0.72, and 0.18.
Close.
0.28.
0.28.
Oh, yeah.
Oh, yeah, no worries. You had the right idea. So now you can go ahead and fill that in. .14. Okay, and I might add a little bit. Okay, there we go. We got a little bit more precision on this one. So keep in mind with this one, it's, what am I trying to say? It's not just a 14.5% chance that we go to overtime, because there are 3 different ways that we could go to overtime, in the sense that he could miss the first, the second, or the third, and it's fine. So we have 3 different outcomes of these 8 up here. So this is where it gets just a little bit more complicated. So what do you think we could do? If we have 3 different outcomes up here where we go to overtime, what can we do to this 14.5% probability?
We just multiply by 3.
That's it. So if we multiply by 3, we can get our answer, and this does indeed. So I'll just show times 3 equals 0.435. And again, there's more precision, but this works for our purposes. So now we're really looking at 8 different possibilities of way these free throws could go. And what's the overall probability of getting a specific outcome? So now we've got lose, and we can see that losing would be either any of those 4 scenarios, but we've got where he only makes 1 or he makes none at all. And we need to figure out those probabilities separately. We can start with missing all 3. So minus and minus and minus. So that is going to be, I'm just doing this one quickly. You guys can go ahead, plug the numbers in your calculator so you're ready with the answer. And you can plug that number in. Okay. So he's got some possibility of missing all 3. But more importantly, if we look at the next one, maybe he only makes 1. And it doesn't matter right here where we show the make. That's going to be your 0.72 times 0.28 times 0.28. I'm not giving myself tons of room for this, but we'll make it work. All right. So because just like before, and I am doing this a little bit quickly, but because we have, if I focus, I'll change the color real quick. If I focus on, I didn't change the color. There we go. If I focus on the fact that there are 3 outcomes right there that lead to only 1 make, then I can do just what we did before, multiply this times 3, and we can get our probability for that. So if you can squeeze that in the bottom underneath. Or if you want, you can just, oh, there we go. We're getting the answer. There we go. And it depends on how you round it. It's going to be about 16.8, 16.9%. All right, now, of course, the last thing to do, we have 2 different probabilities. What do we do with these 2?
Multiply them.
Well, in this case, these are mutually exclusive outcomes.
So wouldn't you add
either
them?
one of them. So we're going to just add them up, and either one of these outcomes, where making 1 or making none, can be added together because they both mean a loss. And I'll just put this right here. Okay, I'm getting, let's just say all that matters is a 19.1%, which it'll be about that. All right, you might be a little bit off from there. And we did do some rounding. So if we kept all the precision, we would see this adds up to 100%. But let me put these yellow boxes around the 3 that matter. So there's a probability of overtime, of losing, and here's the probability of winning. So the odds are looking pretty good right now. So this is not too bad right now as far as, yeah, this took some time. But mathematically, we can work through all the different steps it takes to get our answers for the probabilities. Now, this gets way more complicated if we're looking at a situation where me just move something over real quick, sorry. This gets vastly more complicated if we're looking at a situation where he was shooting 10 free throws, because then we have so many different options that are like, oh, well, he could make all 10, he could make only 9, 8. And then when he gets to 5, he has so many different ways of only making 5. So that is really, really complex. And we get into what we call this fancy function, which is your choose function. And this is something that you might have seen before. In fact, if you go to math on your calculator and over to probability, like you've done before for your random integer, notice that third one, NCR. So this is your combinations versus NPR is for permutations. So you will probably have a chance to work with that if you do like discrete math at some point in your life. So permutations and combinations, we're looking at what's called a choose function. And with only 3 events, doing this choose by hand isn't that hard. But I'm going to erase all this real quick up top. And really kind of the key thing is that, well, maybe the easiest way of thinking about it is that there are lots of different paths. Let me just formalize it a little more. I'm trying to figure out the best way of getting this across to you. I'm going to clear the whole screen. We've got our numbers and we'll get those later anyway. The choose function works like this. So I'm changing my mind of how I want to present this. So I'm going to go back to this page. The way this works is the N represents the number of trials. So in this case, we had 3 free throws. So this would be 3 choose, and the K represents how many successes are we looking for. And so 3 choose 0 successes would mean that there's only one outcome. If I shoot a free throw 3 times and I miss all of them, then there's only one way that happens. That's I miss, and then I miss, and then I miss. Now, if I wanted to do, and that would be represented by this, minus, minus, minus. If I did, let me change this a little bit. If I did 3 choose 1, then that's where I could make the first one, miss the second 2, and then so on like this. So 3 choose 1 means that I have 3 different outcomes. And we can actually do this on our calculator. If you go to math, and you don't have to do this right now, but if you do in, actually, there's a specific formula. You need to put in your 3 first, and then do your math in choose R, and then you can put 1. You'll see it gives you 3. It looks kind of like this on the calculator. I'm jumping a little bit ahead when I do that, but if you see what my calculator looks like, it's 3 in choose 1, and then I get 3 as my answer. But we can see this on paper too. So now if I'll try the next one. 3 choose 2, that means 2 successes. Okay, and there we can see that's also going to be 3 outcomes. And finally, 3 choose 3 would be only 1 success. That's where I have to make all 3 in a row. So there's only 1 outcome. So it's good to look at it this way. And what you'll find is that your biggest number is going to be whenever you get halfway. So like if I had n choose, if I did n divided by 2 right here and got the halfway point, then that's going to be my biggest number. Because you'll see in the middle is where I got the 3s, and on the ends, it's only 1. On the end, it's always going to be 1. So if I had like 20 choose 10, that's going to be a very big number. All right, and you can plug that in your calculator if you want to see what that number is, or we can look at Pascal's triangle to figure out what that's going to be. So this is really, really cool. I think this is kind of a brief aside, but it's worth talking about. We talked about Pascal's triangle in the past when we were talking about the normal distribution, But now we're going to talk about in terms of, it's really better described as a binomial distribution, okay? Because we can treat every single path, left or right, as a failure or a success. So if I go to the left, I'm going to consider that a failure. If I go to the right, I'm going to consider that a success. So if I have 3 choose, and notice we're looking at this row, 3 choose 0 is going to be I fail, then I fail, and then I fail, and I have only one outcome. Or maybe it's 3 choose 1. So I'm going to go to the next one over. So now I could succeed the first time and then fail twice, succeed the second time, or succeed the third time. And there's only 3 paths to get there. So what these numbers represent are the number of unique paths that we can follow to get to that particular node. So this is really good. If you look down here, 5 choose 2 is right there. So that's going to be 10. And I'm not going to try and find all 10 paths. What might be a little easier is if I look at this one, try and find 6 paths to here. I could go fail, fail, succeed, 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 fail, fail. And then succeed, fail, succeed, fail, fail, succeed, fail, succeed, fail, succeed, succeed, fail, succeed, fail, fail, succeed. So there's all 6 paths. And so the Pascal's triangle can be summarized this way as just a whole set of your choose functions. And this is another notation for it. I'm sorry, I didn't really point that out ahead of time. If you see the notation like this, that's the same as when we were doing in choose k, that'd be the same as in choose k with the numbers like this. So that was probably a little bit confusing at first. I apologize. All right, have a good one. So there we go. This choose function is going to be very important because it's going to come into play when we get into our binomial distributions, which is the main thing for today. Maybe that we'll call that good for now. Binomial probability. Let's first of all talk about this. We have the probability. We're only going to look at the probability of getting to overtime. That is, I'll just start this off. This is 2 successes. And what's the probability of success? We're going back to our free throw shooting example. What's the probability of success?
0.72.
0.72, which means 0.28. So I'm going to figure out the probability of overtime now without using that, table that we created. In fact, I'm going to use this formula right here, which looks complicated. It does. But we'll see it's really not so bad. Because this right here is going to represent n. This is going to represent k. Sometimes it's r, like on our calculator, they use r. This represents the p, which is the probability of success. And this, now in your book, they use q for the probability of failure. I don't actually like that because AP formula sheet uses just 1 minus p. That represents 1 minus p, which is your probability of failure. So we're going to see this 1 minus p a lot moving forward. So let's get used to it. So I can just plug this in. So it's essentially going to be the probability of my random variable equaling 2 is going to be, I can write this notation however I like. So it's going to be in choose k, it's going to be 3 choose 2 with the probability of success is 0.72 raised to the k power, which is 2. And then it's going to be 1 minus p, which is 0.28 raised to the n minus k. Well, that's just 3 minus 2, so 1. So basically these two right here have to add up to n. Hope I'm not losing you guys today. I hope this is making sense as we go through it. So this is a way that we can calculate this right away. So we can, first of all, like I said, if we're using our calculator, to do a choose function, you want to put your in first, if that makes sense. So I have 3, so I'm going to put 3, and then I'm going to go math, probability, I can do the NCR option 3 on that one, and then choose 2. We already know the answer to this. N choose 2, sorry, 3 choose 2 is going to be just 3. We already worked that one out by hand. But you wouldn't know it if it was like 16 choose 7, and that would be a huge number. All right. So if we know this first part right here is just 3, then I can multiply. I can just plug this in my calculator, really, if I do it correctly. All right, so I just plugged this formula into my calculator, and I got 0.435456, which is exactly what we had before when we worked it out by hand. Are there questions on this before we move ahead? Okay.
Wait, so how do you get that in the calculator again? The 3 choose 2?
Okay, so what I have to do on my, so if I imagine this box is my actual calculator screen, I have to first of all type in whatever my N is. So I'm going to put in the 3, and it's just going to be sitting there, 3. Then I'll be going to math and the probability menu, which is on the far right. And then I have to choose function 3, which is NCR. So now after I do that, it's going to be NCR on the screen. And then I can just put in a 2. All right. Hopefully that answered it for you. Any other questions? Okay. And I'll also tell you, luckily, we don't have to even deal with this formula for the most part once we get past today. All right. So we've already calculated the first one prior to watching any shot. And I think I'm going to skip over actually watching the videos of this because it won't come through much anyway. Prior to each shot going in, we want to figure out the probability that Memphis wins, loses, or ties. All right, so let's see here. Before the very first one, we've already worked out these probabilities, so I'm just going to copy them down. This was the probability of tying was 0.435. The probability of winning was like 0.37, and this was like 0.191. Close enough to that. Okay. Now I will tell you, he made the first shot. This is a real situation. With all the specifics, you imagine it would be real. He made the first one, so it was 74 to 75. There were 2 shots remaining. So now, before he takes the next shot, we can figure out the probabilities at this point. In order to win, he needs to make 2 shots. And I'm going to go through this part a little bit fast. So he needs to make the first one and the second one, which is just going to be 0.72 times 0.72. Which is 0.5184. This is pretty good. Pretty good. The probability of a tie is if he only makes one. So he could make the first one and miss the second, or he could miss the second and make the first. So I'm just going to do, this is the same as 2 times, because there's 2 different outcomes here. So that's going to be 2 times 0.72 times 0.28. So if I do that, 2 times 0.72 times 0.28 is 0.4032. And they only lose if he misses both, which is just 0.28 times 0.28. So they're in a good spot right now. And that is 0.0784. Okay, so spoilers. He misses the second free throw. So it's still 74-74. At this point, the only thing he can do is make that last free throw and tie the game. So their probability of winning at this point is, well, let me just put, probability of win is 0 after the second free throw. The probability that they lose, well, this one's really easy to figure out. What is the probability at this point? There's one free throw left. What's the probability that they lose the game?
0.28.
0.28. It's just the probability that he misses once, which is 0.28. So that means the probability that they tie is 0.72. And I won't show you the final shot. What do you think happens?
Probably a tie.
Probability would tell us that, but that didn't happen. He missed the shot.
Wow.
They lost the game. So they went from a, just based on these statistics, you know, at one point they had like a 92% chance of winning the game when he had 2 free throws left, or tying or winning the game. And anyways, that's what happened in real life. So now the question, if we go back just up to here, that very first one, Washington, this Darius Washington, the guy who was fouled, he was a 40% free throw shooter. So there's a 40% chance that he was going to make the shot and win the game. So was it smart for Louisville to foul? We don't have to dwell on this one too long. This is almost an opinion question. I mean, you need to have some statistical reasoning, but to be fair, their odds of winning did go down just a little bit. It went from 40%, had he made the three-pointer, down to 37%. It changed by a little, but what it did was it also gave him a greater opportunity to be able to tie the game. So this is one where you can kind of argue either way. So if you're just looking at winning or not, then it was maybe smart for them to foul. But if you think, well, yeah, but you gave him an opportunity to tie the game, then it wasn't as smart. All right. There we go. So we're looking at binomial distributions. And hopefully that anyways, let's just run through it. The distribution of outcomes for binomial depends on only 2 numbers. It's the number, n is the number of trials, so that's when we're doing our n choose k. And p is the probability of a success. Now, let me go ahead and pull this up real quick. And we're looking at binomial distribution. I'm going to begin an analysis right here. So if I go back to this scenario, there are 3 free throws, and there was a 0.72 probability of success for any given free throw. And look at what we have here. We have this. Now, these numbers don't mean anything when you first jump off, but we calculated by hand the probability of him making 2 free throws and tying the game. Well, I can figure that out right here. The probability of exactly 2 successes is, look at that, 0.4355. That number should look familiar. Now, we could also figure out the probability of them winning. And we calculated this. We said it was about 37%. He needed 3 successes for this to happen. And look at that. The probability of winning is 37%. And then losing would be if he had 0 or 1 success. And there is 19.1% chance. So this binomial distribution, I can play with this. So I could come up with all kinds of different things. What if I flipped a coin 4 times? And I wanted to count how many heads I ended up with. So there's, sorry, 0.5 is the probability. So this is it. So if I want to figure out what's the probability I can get 3 heads, well, I could figure out the probability of getting exactly 3 heads out of 4 is going to be 25% chance of that happening. Okay, which might seem like higher odds than you expect, or maybe it's about in line with what you expect. Now, here's another scenario, if you can follow along with this. Imagine I give you 12 dice, and I said I would give you some money, however much, if you could get 3 6s. It always comes back to gambling in this class, I guess. So, so if I give you 12 dice, what's the probability of getting a 6 on a die? Well, it's 1 in 6, which is 0.166, repeating. So there we go. So there's your probability of a success. Here's 12 dice. That seems like a pretty good deal. What's the probability you could get 3 or more? So I'm going to say the probability of getting anywhere from 3 to 12 successes, it doesn't matter. Look at that. There's only a 32% chance that you would actually succeed. If you want to test this out, get 12 dice at home and do this about 1,000 times. Let me know if it happens about 32% of the time. All right, but statistically, that's what should happen. Okay, so this is where the binomial distribution is really helpful. We can figure out if we have Bernoulli trials, which is everything either succeeds or fails, all the trials are independent, and we have the same probability for each one, then we can use the binomial distribution. And okay, actually, I didn't show that this is unimodal. So it is always going to be unimodal. Now, if I bump this up big time, let's say that we had 1,000 trials, and we had like a 0.4 probability. Look at that. That looks quite normal. 1,000 is even too much. I could just do 100. Now it's an approximately normal distribution, but you have to get up, and we're going to dig into that more later. So let's kind of talk about the takeaway from this. What is the actual practical takeaway that we need to know for today? We need to know if it's appropriate to use the binomial setting. And it must meet 4 criteria. It must be a Bernoulli trial. It must be binary and independent. The extra condition is that we need to have a limited number of trials. So if I say you're shooting 3 free throws, how many successes are you going to have? That would be a great case for using a binomial setting. S means the same probability for each trial. And just to clarify this, because where some confusion can come in, these two can seem like they're the same thing. Well, they're independent, which means the probability doesn't affect. The same probability means that we're doing the same thing over and over again. So in a situation where I flip a coin, then roll a die, those are independent, but it's not the same probability. All right, so that would not qualify for using the binomial setting. So really you want to look for the same event being repeated over and over, and how many successes can you get out of X number of trials. So we're going to, so again, keep in mind it's bins right here. Is it binary? Is it independent? Is it a set number of trials? And do we have the same probability each time? So I'm going to give you guys some scenarios, and I'll put this down here at the bottom. I'm going to shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. I'm going to repeat this process 10 times. And X is going to represent the number of aces that I observe. Is it appropriate to use the binomial setting? So let's, instead of just trying to say yes or no, let's go through it step by step. Is this binary? Each event, is it binary?
Yes.
It is. So what does success mean?
You reveal an ace.
There you go. Success is an ace. And then a failure is not an ace. All right. Is it independent?
Yeah.
It is. I'm putting the card back in, so the probability never changes. And I have replacement. So yes, it's independent. There's replacement. Okay. Do we have a set number of trials?
Yes.
Yes, we do. We're going to repeat it 10 times. So n equals 10. So we're good there. And lastly, do we have the same probability each time?
Yeah.
Yeah, we do. And what is that probability? It's okay if there's not as much familiarity with decks of cards. So 4 aces out of how many cards in a deck?
52.
There it is, 52, which is 1 in 13. We have a 1 in 13 probability each time. All right, so that scenario, we have met all the conditions. We can use binomial setting. And I know you don't know what that means once we move beyond bins, but we will talk about that today. Okay, here's your next scenario. Okay, so the first one, is it binary?
Is it supposed to be a success if they're over 6 feet tall?
There you go. Success is greater than 6 feet, which means, I guess less than an equal to would be a failure. Is it independent?
Yeah, I think so.
This one's a little bit tricky. It's probably not independent because when we are picking people from the class, if I pick, in this class, there's only 10 people or so. So if I pick one person, then out of the next one, there's only 9 people to pick from, right? So we're not using replacement here. So because I'm not using replacement, I can still do probability with this scenario, but I can't use binomial probability. We have failed at this. Now we can finish this out. Do we have a set number of trials?
I think just one trial.
Well, since it's 5 students, that would be the number of trials.
Oh, okay, yeah.
Yeah, but you were thinking through it. So we are good on that. And the same probability, this is where we fail also, where the probability changes. So I'm not going to put anything there. So this would not be appropriate to use a binomial type of calculation. This, we can't do bends on this one real quick. All right, Pedro drives the same route to work Monday through Friday. His route includes 1 traffic light. According to the local traffic department, there is a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 of Pedro's work days at random and let y equal the number of times that the light is red out of 10. So, is it binary?
Yeah.
It is. What is success here?
Red light.
Yeah, and keep in mind, this is where success and failure is all relative to our problem. Now, we would probably consider that a failure if we ran into a red light, but it's a success in our particular problem. All right, is it independent?
Yeah.
Oh, well, there you go. Yeah, these are random days. We can assume it's independent. So I'll just say random. So we're good there, good there. And random on its own doesn't mean it's independent. I want to make sure that's not synonymous, but maybe I should have put something else. But yeah, they're independent. Do we have a set number of trials?
Yeah.
Yes, we do. And how many is that?
10.
Okay, and last one. Do we have the same probability each day?
Yeah, 55%.
There we are. So this is not so bad. All right, so running through bins and making sure it's appropriate. So it says explain why it's a binomial random variable. Well, we already did that because it met bins. We're good to go. So now we want to figure out the probability that the light is red on exactly 7 days. And to do that, I'm going to use that formula that we introduced. It says the probability that X equals a specific value is going to be in choose K times the probability of success raised to the power of K times 1 minus probability times n minus K, or raised to the n minus K power. And I believe this is on your AP formula sheet. In fact, I'm almost certain that it is, but we will also do a lot of math where we don't need this formula. Today we will. So we want to figure out the probability that our random variable equals exactly 7. And we're going to say we have 10 trials. So if I kind of show this, n equals 10, I already have it written over on the other side, but I'll show it again. K represents 7 successes. Our probability is 0.55. And our 1 minus the probability, these are the only numbers we need, is going to be, therefore, 0.45. So you can plug these numbers right in. I'll do that real quick. Okay, here's 7. All right. So, and whenever I show you guys, like with most things, when I show you the easier way of doing this, rather than using this complex formula, you're going to hate that you had to even use this formula, but it's good for us, right? So I'm going to start by doing the 10 choose 7. We're going to see what this number is. This is going to be a big number, I can tell you that. 10 choose 7. So I'm going to do 10, put that number in, then do my probability, then option 3, 7. Well, it's not as big as I thought it was going to be. What number did you guys find?
120.
120. There we go. These can grow really big, really fast. So anyways, now we can plug in the rest of the numbers on your calculator. So go for it. You can do that independently, I assume. And as soon as you have your answer, I will leave a blank up here and you can show what you got. So put your answer right there and you got it. Okay. So there we got it. About a 16.6% chance that he will get exactly 7 lights out of 10 random days. So did it out of exactly 7? I don't know what I said out loud. Exactly 7 days out of 10. So this might seem like a random question to try and answer. Like, do we really care that he gets exactly 7 days out of 10? And generally speaking, no, we wouldn't care about this, but we might care a lot about what's the probability he gets 5 or more. And we're going to talk about that tomorrow. But right now we're just talking about getting exact values. So I'm going to clear that. We can move forward. And we've got, now I might skip over this just for time's sake. If you want to come back to this to make sure you understand how to identify if it's a Bernoulli trial, we can look at that. But this is a good kind of question just to go through and make sure it's an appropriate setting to use binomial. All right. I think it's worth talking about this one. This is just a conceptual question. The Department of Transportation report about air travel found that airlines misplace about 5 bags per 1,000 passengers. Suppose you're traveling with a group of people who have checked out 22 pieces of luggage on your flight. Can you consider the fate of these bags to be Bernoulli trials? And why or why not? So I guess the question, without running through all 4 of them, is does this meet all conditions? And if it doesn't, which condition does it fail with?
So the Bernoulli trials, is that also BINs or is it just BIS?
Well, that's a good question. Sorry. Yeah, I shouldn't include the in. Good catch. I was just so used to writing bins. So does it meet all 3 of these? If not, where does it fail? So let me ask this. When we have a rate that says that 5 bags per 1,000 passengers are lost, do we think that those are scattered evenly across all flights? Or do you think there are some flights that have a lot of missing luggage and some flights where all the luggage is accounted for?
Not scattered evenly.
Right. So if we wanted to turn this to a very macabre kind of analogy, if we're talking about deaths in airplanes, there might be like, 1 in a million passengers dies. But I can guarantee you that if you're on a plane where 1 person dies because of a plane crash, it's not independent. You don't get to just count on those statistics, right? You're probably going to die too. Now that's a very morbid kind of analogy here, but I think that's the idea. These aren't really independent. So maybe that's where this fails as Bernoulli trials. But if we were talking about people scattered, like we picked random airline passengers across the millions of people who fly in planes every year, and we just picked random people from all flights, that would probably be acceptable. Okay, this is the last thing we're doing today, and we only have a few things we can do. So let's skip over. The only thing that we're going to miss, that we're going to look at, is this right here. These 2 problems. And I need to get my book out. I forget her probability of success. I think she's like a 90% bullseye shooter, but I forget the number. So this is chapter 17, what number does it say? 18. She's an 80%. So here we go. One thing that's not mentioned here is that she can hit this, our archer, she can hit the free throw, man, I'm mixing all my stuff up today. She can hit the bullseye 80% of the time. All right. So what's the probability that she never misses? So let's fill this in. What is our N for this problem?
10.
10. We got 10 arrows that are being shot. So we got 10 trials. What is the K for this particular problem?
10.
10. We want to see the probability of getting 10 successes. And the probability of failure will be what?
Point 2.
0.2. So here we are. We've got now this formula, the probability of x equals lowercase x right here is going to be n choose k. I'm just going to put the formula out, and then I want you guys to plug in the rest, and I'm just going to put equals, and you guys can tell me what you got for an answer. So put your answer on that blank once you've plugged everything in. All right, so any questions on that one? If you've already done that one, you can try part 3 too. So now I'll just put in another blank right here. So the same thing equals blank. And I want you guys to go through, and as soon as you've figured out the probability of getting exactly 8 bullseyes, then put that number in. Okay. So hopefully everyone had plenty of time to figure out how they would have plugged this into their calculator. I will just go ahead and show you the formula that you should have had. I want to figure out the probability that my random variable equals x exact, or 8 exactly. And we've already determined here. Now, technically I skipped over that step, but we probably already know that this worked as for the binomial setting. But it is binary. She either makes the bullseye or she doesn't. It's independent. We're going to assume each arrow shot is independent of the other. We have a set number of trials. There's 10 arrows, and we have the same probability each time, 0.8. So we want to find the probability of getting exactly 8. So I'm going to do 10 choose 8, and I want to do the probability of 0.8 raised to the power of k, which is 8. And then it's going to be 1 minus the probability, which is 0.2 raised to the whatever's left over. So that's kind of, I know it says n minus k, but it's whatever's left over out of 10. Because remember, these two have to add up to n. So once you plug that into your calculator, 0.302 is the same answer that I got. So must mean it's right if 2 people got it. So there we go. That's kind of the main takeaway for today. If you are still struggling with anything conceptually or with the math of it or the calculator part of it, please let me know. Your homework right here is found right here. Look at this. You're already on page 400 of this book. How crazy is that? And chapter 17, read through that because you'll learn about a lot about Bernoulli trials and binomial probability, all this fun stuff. So anyways, if you have questions, stick around. If you are good to go, have a wonderful day, and I will see you tomorrow.
Thanks, Mr. Davis.
Thanks, Mr.
Have a good one.
Thank you.